Hi, welcome to the video for Module 13. This video will talk about how we can test for an association between two variables. We're going to focus on comparing groups when we have a quantitative response variable. When we're comparing groups and we have a quantitative response variable, we use a categorical explanatory variable to form two groups. Then we calculate the mean of the quantitative response variable for each of the two groups. And our sample statistic, which is going to give us a measure of how big the difference is between the responses in the two groups, is going to be found by taking the difference in the mean, so subtracting one mean from the other. An example from the activity we did in the last module, we were looking at whether arthroscopic partial meniscectomy has an effect on knee pain after exercise. We were looking at, if you remember, we had over here, we had people who were randomly assigned to have either real surgery or a sham placebo type surgery, and we have their pain scores measured on a 10-point scale. The mean pain score for people who had the sham surgery was 3.1, and for the people with the real surgery was 2.5. So the difference in those two means is 0.6, where the average pain score is 0.6 higher among people who had the sham surgery than among those who had the real surgery. So next thing we need to know is this difference statistically significant? And the way we're going to decide is by using a hypothesis test. Now, to have a hypothesis test, we need to have the null and alternative hypotheses. The null hypothesis is always going to be that there's no real difference in response between the two groups. The difference we saw was just because of chance. The alternative is that there is a difference in the response between the two groups that is real. Now, in the context of this example, the null would be that there's no real difference in pain scores between patients who have real surgery and those who have placebo. And the alternative would be that patients who have real surgery have less pain than those who have placebo surgery. Now, to decide if the difference is statistically significant, in our hypothesis test, we're going to need to decide if the sample statistic we observed, that was that difference in means of 0.6 in this case, that sample statistic we observed would be very unlikely to occur by chance if there's no real difference in response between the two groups. Right? That's what we need to find out. Now the p-value, remember, measures the chance of observing a sample statistic like ours, so a difference as large as our sample statistic, or even a bigger difference, if in reality the response has nothing to do with the explanatory variable. That is, in our situation, that the pain score has nothing to do with the type of surgery that people had. We're going to use a randomization distribution to see the kinds of sample statistics that would occur by chance if the response is not associated with the explanatory variable. That is, if there's really no difference in pain scores. So use your intuition and think for a minute about what you think the randomization distribution is going to look like. Where will it be centered? What shape will it be? And how much spread do you think there'll be in that distribution? Stop the video for a minute and think about these things, and then turn it back on and we'll talk about it. Now, because the distribution is simulated to show us the kinds of differences that might be observed just by random chance, if in fact there's no true difference between the two groups, the randomization distribution is going to be centered around 0, right? Because the null hypothesis is a difference of 0. The shape is probably going to be bell-shaped because randomization distributions, just like sampling distributions and bootstrap distributions, always tend to be bell-shaped unless the sample size is really small. The amount of spread in the randomization distribution is a little bit more difficult to guess, and that's why we are going to need to simulate the randomization distribution to see how much spread there is. So how can we simulate the randomization distribution? The idea behind how this is done is that if pain is unrelated to the type of surgery that people had, then everyone would have had the same pain score, regardless of which type of surgery they received. If this is the case, then the difference in means that we saw resulted not from the type of surgery that people had, but instead just because of how the groups happened to be randomly formed. And so we can look at other differences that might have occurred just as a result of how the groups were randomly formed. And we use the same sample sizes as in the original data because we know that the amount of variation in the randomization distribution is related to the sample size. Now in StatKey, we can simulate the randomization distribution by going to randomization hypothesis test and then clicking on the difference in means. You can upload your file, which I did, and we can see that over here in the right corner, it shows us the data from the original sample. We have the mean pain score of 3.1 for the sham surgery, the mean pain score for the real surgery of 2.5, and the difference in those two means, which is our sample statistic, remember, calculated up here. So our sample statistic is always up here in the original sample. Now, down below, I've generated one randomization sample. What it did is it took these same pain scores, but divided them up differently so we can see another difference in means that might have occurred just due to random chance of how the people happened to be broken up into two groups of 20. For each of the newly formed groups, the mean was calculated and the difference of means, negative 0.2, is calculated here and then plotted over here on the randomization dot plot. Since one sample is not enough to create a randomization distribution, I've now generated 1,000 samples. Each dot in this distribution, remember, is representing the difference in means calculated from one randomization sample. The sample statistic is still up here, 0.6. You can see the distribution is in fact pretty bell-shaped, and it is centered very close to 0. So just what we thought, and now we have a sense of how much variation there is in that distribution also. Now, to find the p-value, we need to decide which tail is appropriate, and that depends on the alternative hypothesis, whether we're finding evidence that the difference is more than or less than 0. Then we use the sample statistic, which is the observed difference in means from the original sample. And the p-value is going to be the proportion of dots in the appropriate tail that are at our sample statistic or beyond into the tail. So take a minute and use the randomization distribution and try to find the p-value. Now if you have trouble counting all the dots, that's okay, just approximate the p-value. We'll look at how to find it in a minute. Stop the video and start it back up after you think you've got a good estimation of what the p-value is. Okay, so since we are looking to see if the pain scores are higher in the sham surgery than the real surgery, and we subtracted in that order, we've got a positive difference of 0.6. We're going to be using a right tail, and I'm going to find my original sample statistic, 0.6, down here on the bottom. It's somewhere around here. And I would figure out what proportion of the dots are at this point and further into the tail. Now, I'm not going to count all the dots, but it looks to me like it's somewhere around a quarter of the dots that are out there. So somewhere around 0.25. If we want to find the p-value exactly, we can use that right tail button in StatKey. I click the right tail button and put the cutoff on the bottom at 0.6. You can see the actual p-value with StatKey counting all the dots and dividing by 1,000 is 0.260. So there's our p-value. Now we're going to use the p-value to draw a conclusion from our test. So we had our null and alternative hypotheses, and our p-value is 0.260, which is larger than 0.05. So we are going to fail to reject the null hypothesis. When we fail to reject the null hypothesis, it does not mean that we have evidence that it's true. It only means that we don't have strong enough evidence to refute it. So what we conclude is that there is not strong evidence that patients who have real surgery have less pain than those who have placebo surgery. That is, there's not evidence that the surgery is effective at reducing pain. The next thing to do is to complete the module activity and ask questions if you need to. Then check the solutions, and again, if you find that there's something you're not sure about, make sure you ask questions, and then you can complete the module quiz. Thanks, have a good day.